Yeah, so if you don't want to be recorded, yeah, please go ahead and turn off your camera. But we are recording right now. So, all right. So welcome to the Austin Python Meetup, our fifth meetup for 2021. Thank you everyone for coming, and everyone from Austin and from around the world. Today we have two great presentations. The first presentation or the first talk will be about executable storytelling with rule-based models. And the second one will talk about Python versus the pandemic, writing high-performance models in Jiffy. We have two great presenters today. Our first presenter is William Waits. He's joining us all the way from UK. Thank you so much. I truly appreciate it for staying so late and doing this for our community. William is an internet engineer, retired to academia. He did some PhD work at the intersection of computation and theoretical biology at the University of Edinburgh. School of Informatics, and is now a research fellow at the London School of Hygiene and Tropical Medicine in the Center of the Mathematical Modeling of Infectious Diseases. Our second presenter is Dr. Cliff Kerr. I hope I pronounced your last name correctly. He is a senior research scientist at the Institute of Disease Modeling, also known as IDM. Which is part of the Bill and Melinda Gates Foundation. Prior to joining IDM, he taught scientific computing at the University of Sydney, co-founded two startups, worked on a DARPA project teaching robots how to pick up balls, and wrote an algorithm to translate real-time brain activity into music. Cliff, you need to talk to me after this, how you do that. So we'll start with the first presentation. William, tell us more about executable storytelling with the rule-based models. William, the floor is yours.
Thank you very much, Florian, and greetings from Edinburgh, everybody. Let me see if I can. Yeah, Jacob's waving. Let me see if I can share my screen. Say share, and now we're looking into a kind of kaleidoscope. And here, can you see that?
Yes, we can see it.
Excellent. Okay. I hope I'm not overselling this with the title, but well, we'll see. So, what am I gonna tell you about? I'm gonna start, because it's late in the evening and a good time for philosophizing. I'm gonna talk a little bit about what models are, what I think they are, how I think about them. Show a simple, sort of just basic model that you would find in epidemiology, although I'm not going to describe it in the way that it always is treated. And then I'm going to show something a little bit fancier, how you can go further with this. Yeah, so models. What are models? So this is a picture of a train. It's a picture of three models of a train that I found on the internet there. And what do I want to say about this? Well, these are not real trains, right? These are model trains, and we all know what model trains are like. They're in different sizes, so kind of at different levels of granularity. The big one has a lot more detail than the small one. So we can imagine that we've got three different models of train, and the models are more or less detailed. And it's very much the same when you're making mathematical models of things in biology or populations or epidemiology or that sort of thing. I mean, they're not pictures of trains, obviously, but, the level of detail that you choose is a choice. when you're making these models, and it's an important choice. This has to do with getting the level of abstraction right for describing what problem you're thinking about. And I guess abstraction is something that we think about in programming in Python and other languages all the time. If you get the right abstraction, you end up writing a very nice, elegant program that captures and does exactly what you want it to do. And if you get the abstraction wrong, you're in it's kind of no end of trouble. Models in epidemiology, what are they for? Because, we've heard a lot about these, right? They've been in the news for the past year, and people are models of this, models of that. There are a few different things you can do with the models, right? One thing you might want to do that everybody wants to do is you might want to predict the future. And this is hard. You just think of predicting the weather, right? You use the same kinds of models for predicting the weather, and we can get a forecast a few days out, maybe a week, maybe 2 weeks if you're very, very lucky. Beyond that is pretty much impossible. But people want to try to use models for prediction. Another thing that you can do with them is you can use them for explaining things. Right? This is different from prediction, although it's connected, because if you have a model that you think, this represents something that's going on in the world and it explains it well, it's, a sort of a convincing account of what's going on, well, you might only believe it's true if it can at least try to make some kinds of, predictions that match reality. Otherwise, it's just, a nice little clockwork. A third thing we can do with them, which we do quite often, and I think Cliff will talk about this in more detail, is you can use models for exploration. Right? You can say, what if? And you can do this. It's nice. You can do this in computers with mathematical models and computational models. You can do things that you could not do in the real world, right? There are a whole bunch of what if kinds of questions that you would ask. What if we make some kind of an intervention? What if we, in thinking of infectious diseases, what if we, if we vaccinate these people first or those people first, what do we think is going to happen to the trajectory of the epidemic and all the different things we might want to measure? So we can use models for exploration as well. There's actually a fourth thing that I didn't put on this slide, and it only occurred to me afterwards. You can use models for describing. Statistical models are very much about description, right? Statistical models are not especially good at explaining why things happen, but they are very good at explaining what happens if you pose them correctly. Explanatory models are the kind that I like to work with most, and so we'll maybe think a little bit more about what that means in the slides to come. So okay, let's start with the kind of standard. There's a couple of slides of mathematics, but the mathematics is no more than this. What's on this slide here? The sort of standard way, the basic infectious disease model, it dates from Kermack and McKendry in Edinburgh and Aberdeen, in fact, just here in about the early 20th century. One of them, I can never remember which one, was a biochemist. And that's important because if you look at the sort of pair of equations on the top here, all three represent exactly the same thing. Well, if you look at the pair of equations on the top, they look a little bit like chemical reactions that maybe you remember from high school, right? And what does this say? The one on the left, the one that says, S plus I, well, S, what does this mean? This means somebody who's susceptible and somebody who's infectious. And if they bump together, if they have some kind of contact, there's a chance and there's some rate for turning the susceptible person into an infectious person, right? And this is the process of disease transmission is what this describes. On the right, on the top, there's the next step, right? The next step when somebody who is infectious then recovers or well, in the original model, perhaps recovers, or perhaps dies, unfortunately, but is in any case removed from the system and doesn't participate anymore in this interaction with susceptible people of, transmitting the disease and infecting them. If you look at number 2, it's exactly the same thing, written out in a slightly different way. These are called Petri Nets. Also invented by Carl Petri to study chemistry, and it gives you a little bit clearer idea of what's going on, right? You have, these round things which you can think of as what they're called places, and you can imagine that there are normally called tokens, but you would imagine individuals, people are in these, it's not physical places, it's, the place of being susceptible or the place of being infectious, and the round boxes are transitions, right? And so this says, we'll just take one of them, it says, this beta transition here. It's got 2 arrows going into it, one from susceptible, one from infectious. And it's got 2 arrows going out of it. And the arrows that are going out of it, 2 of them go to infectious, right? And similarly for the, for the recovery transition. And the nice thing about if you write things down, or if you think of them as these Petri nets, is you can identify the 2 places that are called I and stick them together. And so you can make, one sort of diagram, number 3 there, of the whole system. And this gives you an idea of how, if you imagine these places have tokens and, you need one S and one I to bump together to create 2 I's, you can imagine how these tokens might flow through the system. And the beta and the gamma are just rates. They just say how fast these things happen. By the way, I didn't mention, but if anybody would like to say something or interrupt me or have a question or anything, feel perfectly free. It doesn't bother me at all. In fact, I prefer that to keeping questions to the end. But in any case, these are equivalent ways of writing down the same process, a kind of basic SIR sort of model. Often what people do is they take this and they make differential equations out of it, right? And they say, well, how fast is our population of susceptible people? This is just a fraction of the total population. How fast are they? Is that changing, right? And you can just read this directly off of the diagram, right? You have a rate called beta. You know that the S, everything going out of everything from S is going out of S, right? So it's going to have a minus sign. It's getting smaller. The susceptible population is getting smaller as people are being infected, right? And you have this rate beta, and you need an S and an I in order to do that. So you multiply them together, right? Because that's how many ways can that happen? Well, that's the number of S people you have and the number of I people you have multiplied together. You can read directly off. That's the only transition involving the S. Involving the I, there's transition. I've color coded them so you can see where they come from, right? The I has, well, it's got one. One I is leaving, and 2 I's are arriving, and at the at this rate beta, and you can simplify that obviously, just standard high school algebra, and you get an equation that looks like that. And similarly for R, people often do this, and if you wanted to take these and write them down in Python, you could do something like this. I put the script that runs this at that URL that's there, and of course I'm using SourceHut and not GitHub because everybody uses GitHub, and Git was never meant to be some sort of giant centralized extravaganza. It's supposed to be a decentralized thing, so maybe it's good to use alternatives. But I'll get off that soapbox just now. So here's a little direct Python implementation using no libraries other than NumPy that just gives you an arrays that you can multiply, right? And I've used the type annotations because I think it's very helpful to think whenever you write a function, to think of what type of argument it takes and what type it returns. That's very helpful for structuring your code and structuring your thinking about the code. So, the first one, SIR, just says, well, here's a state called S, and it contains how many S's and how many I's and how many R's. And I return, this is just exactly those same differential equations written down in Python, right? Just the right-hand sides of them. You can see that directly, just read it directly off. And we can integrate this equation. This is the Euler method is the simplest possible integrator that you have, which basically just says, well, here I am at X, and I'm going to have a little time step called h. And I'm going to start at s, and I'm going to take this, whatever derivative I have, which will turn out when I use it to be the SIR function there, and I'm going to move a little bit forward, h worth forward, h in time. And, a little function called simulate that says, do this for so many steps. And if you do that, you get a graph that looks like this. If you graph the s's and the i's and the r's over time, and this should look pretty familiar by now. Given it over the past year, we've seen curves that look like this a million times. And you can find a number of things out of this, right? You can say, well, when does I change direction? When does I stop growing and start shrinking? Well, that's exactly when the derivative is 0, right? It's neither increasing nor decreasing. And if you set that to 0 and do a little bit of algebra, you can find out exactly where that is, which happens to be, well, the herd immunity threshold they like to talk about is actually 1 minus that expression there with the s. 1 minus 1 over, well, this quantity r naught, which happens to be, we call it the reproduction number, and it's related to those two constants, those two rate constants. It's very simple, just like that. And you can find out where that is, at what level of susceptibility. I should have probably chosen an r naught that was not 2 here, so that it wouldn't be at 0 at exactly half, because that might be a little bit confusing which way it is. But in any case, for this particular choice of constants, it happens to be right there, and that happens. Well, another thing important to noticing here, everybody says, if you say, well, maybe we want to reach this herd immunity threshold and then it'll all be over. Well, it's obviously not over. It's only about half over if you let things go without changing anything, right? And without doing anything to stop it. You hit the herd immunity threshold naturally with no other processes involved. Well, there's still a long way to go. And I mean, you can find all of that out just from those simple equations there. But okay, so this is our this is
Tell them more about the R naught.
What's that?
Tell them more about the R naught, the R0.
Well, the R naught, which it's a bit confusingly written here because it's 1 over R naught, right? So beta is your the chance of infecting somebody per unit time, right? And the gamma is 1 over gamma is the amount of time that you spend being infectious, right? So you just add that up and you say, well, the number of people I'm likely to infect over the time that my rate of infecting people over the amount of time that I spend being infectious is the number of people that I'm likely to infect, right? And that is exactly what R naught means, right? And it's, of course, the constant of the simulation, or a constant of the system of equations, right? It's the ratio of two constants. It is only true, as in you're only likely to have, well, there's a whole bunch of, this is an incredibly simplified model, but this is only likely to be true at the very beginning, right? Because as soon as the number of infectious people, or the number of susceptible people starts going down, there are fewer of them around, right? And so eventually you get to a point where actually, even though I might be infectious in the same way for the same period of time, I just have less chance of bumping into a susceptible person to infect them. So I'm going to infect people, I'm going to infect less, right? Maybe if people have specific questions about that, I'm happy to explain more. But
I wanted them to see where the origin, because most people here don't know what an SIR model is. So it's like I wanted to show them where this R naught is coming from and wanted you to talk about that. This is why. It's mostly for general education, because now they know.
Yes, absolutely. Well, I mean, as I said, I just explained how the SIR model works. I hope that was clear. But if it's not clear, please speak up.
You can go on.
Okay. I will go on.
This was just to show that, so people know why because they hear about this all the time.
Yeah. Well, I mean, again, and I'll try to stay up later, and we can talk at length afterwards. Just to return to the kind of executable storytelling, my idea is, if we turn a few slides, this kind of picture, right, where I say, well, this process happens, and then this process happens, and these things, they look like chemical reactions on the top, or they look like Petri nets in the in the bottom, or we might even call them rules, right? We might even think about these almost as a query, right? Where the left-hand side is a query. Imagine in your mind, imagine an SQL query if you're programming in Python and using SQL databases. You imagine the left-hand side is a query against the world, against the population, that says, well, okay, give me every combination of S and I, of S people and I people. And then, I mean, there's a little bit of detail for how you simulate this. And then, you pick one pair, and you say, okay, that pair is going to be replaced. So I do an update, right? So you can think of the left-hand side of this as a query, and the right-hand side or a select query, and the right-hand side kind of is an update query. Maybe you can describe the operation of this whole system as, well, okay, well, this happens. There's a transmission process. The transmission process works like this. It's there on the left. And there's a recovery process, and that looks like that, and it's on the right. And we'll see some more rules here, because now we're going to do something a little bit fancier. So some colleagues at work made this picture. What is this picture? They took some data that came from a study called Siren that was in hospitals in England, where basically what they did is they did the PCR tests on hospital workers, and they did them regularly, and they found the ones that had become that had seroconverted, that had caught the COVID in the course of the time they were doing this study. And they worked out, okay, when do they think they were first infected? And then they found out, well, okay, what is the probability of having a positive PCR result as a function of time from your, from when you were infected until much later on. And the data that they have is, of course, shown in that kind of, noisy gray cloud. And then they made a statistical model to fit some kind of a curve onto this cloud to say, well, this is the most likely sort of shape of this curve of your chance of getting a positive PCR test. And notice you're much more likely to get a positive PCR test in some window around 5 days. And you start being, it's quite likely that it's maybe 20% likely that, when you're 3 weeks after having been infected, that you can get a positive PCR test. But it changes. It becomes less likely. And this kind of dynamic is not accounted for at all in the simple SIR model. And so I took a look at this and I thought, well, okay, this is very cool. The statistical model doesn't really explain this in any way. And I'm going to try to imagine what kind of a process can we have that will, that could underline, that could generate a curve, something like this. And this goes as follows. I imagine that we have something called ladder rules. Now, this takes a little bit of explaining. These are rules very much like the chemical reactions that we saw. And there are only 3 of them. I'm going to say, well, okay, 3 things happen here. This is, by the way, the very first simplest thing I could think to do, and there's I have a better, more sophisticated one that takes into account things that the immune system does, and antibodies and B cells and affinity maturation and all that sort of thing. That would take too long to explain. So we'll stick with the very simplest thing here. So the first rule says, well, first of all, everybody is going to start off in a state where they will increase their chance of getting a positive result, given that they're infected, right? So everybody's going to start off going up. If you're going up, you're going to keep going up, and the n there is just a number that counts what level you are on this ladder. We'll see a picture in the next slide of what the ladder looks like. And so you start off, you go up. Later on, at some point, if you're going down, you go down. Very simple, right? You go up, you go down. Your chance of getting a PCR response, I mean, that's just describing the shape of this curve, right? You know, it starts off going up, and then at a certain point, it turns around. That's what the third rule does. It says if I'm going up eventually at a certain point, a randomly chosen point, I'm going to turn around and start going back down. And if I'm going up, I go up. If I'm going down, I go down. At a certain point, I turn around, right? And if you were to try to write this down in Python, you might imagine, well, my individual P here, P for person, is an object, and it has a little bit of internal state. It has a direction, whether it's going up or down, and it has a level. It says how high is it up the ladder. And it has some methods that say, well, okay, go up, go down, or, turn around. That's it. That's simple. Nothing more. Just this, this model of these three things that happen. What this kind of sets up is this is why I call it a ladder, right? So if you read this is, if you were to write it down as a Petri net, it would look something like this. If I'm going up and I am in zero, and zero means I have zero chance of getting a positive result, means I'm not infectious at all. I'm not infected with anything. But if I have one, if I'm a little bit infected, well, two things can happen. I can either go up, or I can turn around. And if I turn around, I'm going down, and then I go down, and eventually I go down to zero. If I go up, well, okay, again, I can go up more, or I can turn around. So just this process, you can see why it's more convenient to write things down in rules that look like this than in the whole Petri net, because you can see how it could start getting complicated written down like this. But here, with just these three rules, saying there's three processes, going up, going down, turning around, very simple. And if we do this, if we simulate this, and there's some detail for how you would want to simulate this. Oh, okay. How do you write this down? So here's I have to apologize for a little bit of a bait and switch. So in the following sense. So this is now exactly that same process written down as three rules. Turn up is there's a detail for why it has to be iterating like that, and down, and some observables that say I want to count how high people are up the ladder. This is in a language called Kappa, which is simulated with a simulator called Kasim, which very conveniently has Python bindings. So even though it itself isn't Python, writing this down, you could write down an object like this, but then to make a simulator for simulating this in general would be quite a lot of work. Fortunately, my colleagues in Paris have done this, and they've written Kasim, the Kappa simulator, and there are Python bindings for taking this and running it. And there's some code that I've written that helps do this a little bit more, right? It says, well, okay, instead of just running it once, you're going to run it lots of different times and simulate it stochastically, and you're going to be able to fit parameters to it and all that sort of thing. So all those things that you would like to do with models in general, including models written in Kappa or directly in Python, which I often do, this is some useful kind of scaffolding for using those. But in any case, this is just the same thing. Don't worry too much about this notation, but this is the same thing written down in a machine readable way, such that I can take this and I can simulate it. And I've got those three rules, and I've got a bunch of observables that let me count how high each individual in the simulation is up the ladder, and some initialization. And if you do that, you get a curve that looks like this. Now, this isn't terribly good. As I say, the more sophisticated model does a much better job of fitting, and it works kind of on the same principles, but this is not bad, actually. This is not bad, and there's some nice observations you can make from this, right? if the PCR send, if we imagine first, we've got several different kinds of tests, right? They test essentially the same sort of thing. They test maybe how much DNA of virus you have in you. They might test how many antibodies you have, but we imagine we've got these lateral flow tests that test antibodies, and we say, okay, well, they're not as accurate. And why are they not as accurate? Well, they're not as accurate because they're not as they're not as sensitive. They're not. What does not as sensitive mean? That's what this horizontal dotted line means. It means that, well, it's going to have a good chance of giving you a positive result for a shorter time window when your viral load is higher, actually. And the PCR sensitivity, well, the horizontal dashed line, you get a positive PCR result as long as your viral load is, most likely as long as your viral load is above that, above that line, and maybe the threshold for infectiousness is somewhere in between. So in any case, if you're thinking about the dynamics of testing, incorporating testing with infectious disease transmission models, well, this is a useful kind of facility to have, especially because this curve is generated from a story of, what happens to individuals. And what follows from this is really neat, actually. If you look at, this is a bit subtle. What this shows is each panel is time from day 0 to day, 14. And this shows how likely, if you choose any one of those individuals that all started off at the same place, how likely are they to have, on the x-axis, a particular viral load, either very high or very low, very high to the right, very low to the left. And you'll notice that after a short amount of time, you find a kind of long tail, right? You find many people have no viral load, they're all, recovered, and relatively few people, increasingly fewer as time goes on, have a higher viral load. So in principle, perhaps they're more infectious, they're more likely to get positive results, certainly. And this is not obvious, but it kind of falls out just of this, again, these very simple dynamics, 3 rules, and this follows directly from that. And we can take this. Now, this is neat, right? So we can take this. That was a story of how viral load works, and PCR tests and that sort of thing. You take this and couple this transmission. So this should look, the top line there should look very much like the standard SIR model, right? On the left you have, the kind of orangey colored one might be infectious, and the bluish colored one is susceptible. What does susceptible mean? Susceptible means going up and having no having zero viral load or zero chance of getting a positive PCR result. And at some rate, don't worry too much, at some rate, the point is proportional to the viral load of the infectious person, proportional to n, which means if somebody is very infectious, they're much more likely to infect you. If they're at the peak of their viral load, you're much more likely, and you encounter them, you're much more likely to get infected. If they're at some point where they have low viral load, well, you're much less likely to have, to be infected by them. And what does this do? Well, it says, first of all, we have the same person that was already infectious comes out, and now the one who was not infected is now infected, is now going up, but has a little bit of virus, right? So this is, this essentially says exactly, the intuitive idea of what happens. Somebody comes along, they have some virus, and somebody has no virus, and they bump into each other, and the one with the virus gives a little bit of virus to the other one. Just so. And written down in the Kappa language, it looks kind of like that. And the point is, if we want to recover these ideas, because, certainly people doing infectious disease modelers like to be able to count the number of susceptible and infectious and recovered people. You can do that just by counting the number of people who are in the state of going up with no viral load. That's the susceptible ones, right? The number of people who have gone all the way around, have gone up the ladder and come back down, and are in the state of going down but have zero viral load, well, they must be removed. And the ones that have some viral load that's non-zero, that should say greater than 0, not greater than 1. It's an error. are infectious. And so you can take that, you can take this rule that says, well, how infection works, a theory of how infection works here, this rule, together with the dynamics that cause viral load to go up and then come down, that we talked about, the ladder, and you can do that, and you can, simulate it, and you get a very similar, a very similar set of curves for the susceptible and the infectious and the removed. Those curves are just the counts of these people in the different states as time goes on. And and that's, and we get this, and this corresponds with what we would expect. The time that we expect it to happen in is now registered to the underlying data about how PCR tests work, which is kind of neat. A technical point, but it's useful. And what we've done here, which is also kind of neat, is we've taken a very simple model of how viral load works, and a very simple model that uses that for transmission, and then we've put them together. And so we've composed these very simple models together just by saying, well, I had 3 rules for how the viral load works, and I have 1 rule for transmission. I put them together in this kind of composition, this compositional property of the rule-based modeling it was very convenient, and it makes it possible to construct quite complex models very, very simply out of individual parts that are individually easy to understand, which is incredibly useful, I find, anyways. And thank you. That's all I have, and I hope that's set the stage a little bit for what Cliff will talk about. Now,
so
what do I
what's the
stop sharing?
Kappa language thing you're showing at the end?
What's that?
What's this Kappa language thing?
Kappa language, as I said, is this kind of is this kind of language here, where we can write down these rules.
Okay, and you have compiler from this to Python?
There's 2 things. One is there is a simulator that's actually written in OCaml with Python bindings, so you can just call it. There is also a native Python version that I've written that is much slower, but a little bit more flexible. And you'll find that inside the NetABC package. So yes, you can, if you want, and not only that, but these details here where it says iterate, end iterate, that is not, those are some, that allows you to put a little bit of, notice the syntax is very much like Python, the for I in range, whatever. And that's because the way this is implemented in NetABC is, even if you're running it using the Kasum simulator, it will pre-process it and generate rules for you where it has to, which again is convenient if you have a need to generate many rules that differ only with by a number or something like that. It was actually invented not for infectious disease style modeling, but for molecular biology. I mean, there's a very broad class of models that it can be applied to. It can be used for molecular dynamics. You have lots of population models in ecology and population biology. As I say, infectious diseases and that sort of thing is useful, but that's essentially just a kind of population biology. Well, what else can you use it for? Well, off the top of my head, I'm not coming up with anything specific. But broadly, in things that are biological, ranging from the molecular level to the population level. Yeah, I'm gonna stop sharing, but I'll stick around and I want to listen to what Cliff has to say as well. So
Before you go to Cliff, I want you to actually explain the difference between compartmental models and agent-based models, so they will understand what's happening.
Well,
Giving the overview, and you do this beautifully. So please explain to the audience, because when Cliff will start explaining what he's doing, it'll be important.
So, what is a compartment? So first of all, the nomenclature is a little bit odd because and can be confusing, because sometimes in other kinds of biology, when we say compartment, we mean like kind of literally a compartment, like if you're doing cell biology, you imagine a cell as a compartment that has stuff going into it. It's got chemicals and stuff moving around. And sometimes the chemicals can move from one cell to another. They move from one compartment to another, and that kind of accords with the everyday notion of what a compartment might mean, right? It's a sort of spatial enclosure of something. In infectious disease modeling, compartment is a little bit different. Well, actually, a lot different. Compartment basically is a notional division of the population, right? You just classify people. You classify people in the population and you say, well, some people are susceptible, some people are infectious, some people are recovered, and you call these divisions of the population compartments. And normally, compartmental models, it's normally understood that the way you simulate them, you don't have to simulate them this way, but the way that you simulate them is by taking something. You can write down diagrams like this, or you can write down, often the diagrams that are written, they call schemas, are not as explicit as these ones that are in front of you, that are in front of you just here. They're missing arrows, basically. They're missing arrows, and the missing arrows can be a little bit confusing because it's implicit that, you need an infectious person and a susceptible person, and it's kind of like a reaction out of which come two infectious ones. So if you try to read some of the papers about compartmental models, and they'll be drawn like that, and there's in those kinds of models, there's only ever one interaction between entities. The only entities are individuals, normally people if you're doing infectious diseases of humans, or cows if you're doing infectious diseases of livestock, or anything like that. But the only interaction is one that produces a new infectious person. There's no other interactions. Everything else is just progression. And you can have more complicated progressions. You can go from, the kind of infectious, which means sometimes you have exposed or a kind of latent period before becoming infectious, right? And, you can go from being exposed to being infectious, and you can go from being infectious to having mild symptoms to having severe symptoms, and that sort of thing. But the point is, there's only ever one interaction and many compartments that describe the different progressions, which are just subdivisions of the population. And normally with compartmental models, they're simulated using differential equations like this. This is not the only way you can simulate them.
But those differential equations, they count the number of people in a compartment, correct?
Well, the differential equations count the change in the number of people in a compartment.
Yeah, thank you.
Yeah. You could also simulate this as this may be getting too technical, but you can also simulate exactly the same system, exactly the same model. This is important as well, is often the distinction between what is a model and what is the way of simulating the model gets lost. So you can take the same model, by which I mean the kind of diagram of the, with the boxes and circles and arrows there. You can take that model and you can derive differential equations, and you can call integrating those a simulation. Or you can say, well, okay, I'm going to, remember this is a Petri net, right? So I'm imagining that in the S place, there are a bunch of individuals. In Petri Net speak, they're called tokens, but in the I place there are a bunch of individuals. And you can simulate that literally by choosing. This is as I was describing when I said, well, maybe you want to think of these as a query, a select query on the left-hand side and an update on the right-hand side, where what you do is you actually select out a pair of individuals that you have to treat as some sort of discrete entities in your program. And then you say, well, okay, I'm going to change a label or an attribute or a what are they called in databases? I'm going to change a database cell that says the state of this one has changed, and so that means it's moved from one compartment to another. And there's a relationship between what you get when you simulate that way with these differential equations, and the relationship is that these differential equations reflect the average trajectory of this system, the average thing it will do. And when the population is large, the average thing that will happen is very close to what actually happens. When the population is very small, if you imagine you've only got 10 people, right? Well, this kind of, ds by dt, the rate of change of susceptible people, it might be a small number, right? And you can't have 1.5 people. It doesn't make any sense. So in those kinds of circumstances, when you're dealing with small numbers, you need to simulate this stochastically. Agent-based models are almost always simulated stochastically. Sometimes they can be simulated in a deterministic step kind of clockwork way, like a finite automaton sort of thing. Normally they're simulated stochastically. In principle, they can be quite general in that they can do anything you can do in a programming language. The language Kappa and the language of Petri Nets and the language of chemical reaction style things like number 1 on this screen here, if you really try and do things that are completely unnatural, you can get them to express extremely complicated dynamics, but really the dynamics that are natural to express are much more restricted than what you can do in a general purpose programming language. And so in principle, agent-based models are generally can do anything you like. It can be exactly what an agent is an individual, and it can have some some methods and timers and do what it wants. There's an entire landscape of different kinds of models, I don't know that we have time to go over all of them and the relationships between them, but there are relationships between them, and it's quite interesting. Just to close, I think, it's quite interesting to think of the relationships between different ways of different models. I mean, I started off. I had some pictures of a train, right? A model. You don't have to have a model written in a computer language, right? When you think about the world and you think about, well, I understand the way this works, and that means I can think of what's going to happen in the future. What you're doing is you're using a mental model, right? And that also is a sort of a simplification of reality that exists inside your head that you use to help think about reality and help anticipate what's going to happen. And it's very interesting to think about the relationships between models, which can include the relationships between what I think is going on and what you think is going on. And not only the thinking of relationships between models is not only limited to the sort of technical detail of what is an agent-based model and what is a compartmental-based model and what is a stochastic Petri net and that sort of thing, but you can think about these relationships on a much more general level, which is nice, I think.
Yeah. One more thing, unless someone else has a question. Anyone has a question? Quiet, shy crowd today. I'll ask because I'll be a provocateur here.
Okay.
So you use the term predict. Can you really predict what's going on?
No, absolutely not. What you can do, well, okay. If what you want to say is if what you want is if you think a prediction is a statement of what will happen, no, absolutely not. If what you mean by prediction is a distribution of things that could possibly happen, then yes. Right? We can say there's a variety of things that could possibly happen. There are some things that are more likely than others. You could imagine this. One way of understanding it, right, is just exactly the story. The bifurcating futures, right? Where at each point in time the entire universe splits into possibilities, and you have a whole tree of possible futures, and then you can imagine all of these possible futures. Well, there's some kind of probability distribution over them, right? Maybe they all happen, maybe one happens. I mean, that's kind of that's purely philosophical, but you can think that some branches of that tree are more likely than other branches of that tree, and you can reason about that. And if that's what you mean by prediction, then I mean, yes, we can.
You can predict what happened in that parallel universe, or that you don't even know. This is basically what you're saying. but no, I brought this question out because people use the term predictive analytics, especially related to Python, and people have to understand you cannot always predict, and the term predict is kind of like misused many times. But William explained it well, exactly what's happening. So.
Thank you, Jacob.
No, thank you, William.
All right. Well,
I'm sorry. I've spoken for nearly an hour now. That's.
And people were listening.
Yeah, it's very interesting. Like that. That's why I like these meetups, because we have people from different backgrounds. Like now we know what Jacob has been talking about for all this time. I know he's been doing. This is modeling, and we have a better idea what he's working on as well. All right, well, thank you, William. Thank you for joining us. I know it's probably 2 in the morning there, so we truly appreciate your sacrifice and coming and presenting this to our community. Truly appreciate it. Thank you so much.
It's my pleasure. Thank you very much. And I drank coffee at like 11 o'clock at night, so I'm wide awake. I'm going to stick around for a while.
Well, thanks so much. It is truly appreciated.